So let's talk a little bit about the spin of atomic particles. See this? We used to call them tops. It's actually a gyroscope. This one's made of titanium. Notice how it's spinning and wants to stay upright. That's because of something called conservation of angular momentum. Angular momentum is not an extremely difficult concept to understand. It's just the product of a particle's straight line velocity times its distance from the center of rotation. So let's get out of the atom for a minute. The Earth is spinning, right? In more ways than one. We're rotating. We complete one rotation around our axis every 24 hours. If angular momentum is the product of your linear velocity times your distance from the center of rotation, then the people at the equator have more angular momentum than the people at the North Pole. And that's true. They do. Angular momentum wants to conserve itself. That's why, if you ever watch professional ice skating, you'll see an ice skater will spin on their tip of their skates, and if they bring their arms in, they'll spin faster. And as they bring their arms out, they spin slower, because the total energy has to be conserved. If they bring their arms in, they're decreasing the distance from the center of rotation of their body, so they have to spin faster to keep the total energy constant. When they bring their arms out and increase the distance, they spin slower automatically. They don't do anything to spin slower or faster. It's from the conservation of energy. So what the hell does that have to do with quantum physics? A lot. Let's take an electron. Early models of an electron have it spinning in its orbits around the nucleus of an atom. And that spin is either assigned as positive or negative. Why is there a difference? Electron's an electron. Well, it makes a difference if you're spinning in the direction of your rotation and revolution, or if you're spinning in a direction that's opposite. Right? So we're spinning, we're rotating around our axis on the Earth, spinning in a certain direction, which is clockwise if you're in the northern hemisphere, and we're revolving around the sun. Now, if you were spinning the other way, your energy would be different. Well, electrons have both spins in their revolutions around an atom, so they possess different energy levels. Why is that important? That's how we first started actually discovering, opening the door to quantum physics, is in the movement of electrons. Different atoms have multiple electrons around them. Now, hydrogen only has one, but if you looked at all the elements that are out there, there's atoms with 2 electrons, 4 electrons, 8, 10, 12, 16, 32. But each electron can only occupy one seat. Think of it as a giant theater, and each person can only sit in one seat in that theater. How do we get light? Light happens because of the energy that's released when a spinning electron goes from one orbital level around a nucleus to another orbital level. When it goes down to a lower energy state, it releases the energy it had at the higher, the larger circle in the form of radiation. We often see that radiation is light. When you see a rainbow, that's caused by ionized particles, electrons that are ionized by a thunderstorm in the atmosphere, changing their states, shifting their states, and they create the visible spectra of light. Red, orange, yellow, green, blue, indigo, violet. Did you ever wonder why they appear in that order? Did you ever see a rainbow that was red, violet, blue, green? No, you can't. Why? Why can't we change the rainbow? Why can't we change the order that the colors appear? It's an intrinsic property of nature. The color corresponds to a certain frequency or wavelength of light. The higher the frequency, the higher the energy. As you move from red to violet, you increase the frequency of the light. So it goes up in energy. So each band of light corresponds to a certain amount of energy. Now you might want to ask, well, why isn't it pastel? Why don't they just smear into each other? Why are there these discrete lines? Now you understand the concept of quanta. Quanta is just a fixed or finite, discrete amount of energy. When an electron is in orbital level 2, the second orbital level around a nucleus, and it goes from orbital level 1, it releases a certain amount of energy that corresponds to a certain color. It can't release half that amount of energy. It can't release a quarter that amount of energy. It's got to release the entire quanta of energy. And so on with the third, the fourth, the fifth, and the sixth levels, the transitions between them. So when you look at a rainbow, you're looking at quantized energy. It just happens to form our primary colors. Thanks. Think about that the next time you see a rainbow.